Hello. Today we'll go through the chapter 5 of chemistry. Why are atoms held together in chemical compounds? There must be some forces that holds them together. You have already learned in lower classes that the forces hold together in a compound are the chemical bonds. How are chemical bonds formed between two atoms? There are two ways of formation of chemical bonds: by loss and gain of electrons and by sharing a pair of electrons between the two atoms. In either process of formation of chemical bonds, each atom attains a stable noble gas electronic configuration.
According to Lewis,
the atoms can be pictured in terms of a positively charged kernel, the nucleus plus inner electrons, an outer shell that can accommodate a maximum of 8 electrons. This octet of electrons represents a stable electronic arrangement. Let's go ahead with the explanation of this now. Cossell and Lewis approach to chemical bonding. Octet rule. Octet rule is based on stability of noble gases due to the presence of 8 electrons as represented by
Ns2np6
in valence shell. This rule states that during the formation of chemical bond, atom loses, gains or share electrons so that its outermost orbit, valence shell, contains 8 electrons. Therefore, the atom attains the nearest inert gas electronic configuration. Ionic bond. Formation of sodium chloride, NaCl. Sodium has 1 electron in its valence shell. It has the tendency to lose 1 electron to acquire the configuration of the nearest noble gas, Ne, 2,8. Chlorine has 7 electrons in its valence shell. It has a tendency to gain 1 electron and thereby acquire the configuration of the nearest noble gas, that is Ar, 2,8,8. During the combination of sodium and chlorine atoms, the sodium atoms transfers its valence electron to the chlorine atoms.
Sodium atom changes into Na plus ion, while chlorine atom changes to chloride minus ion.
The two ions are held together by strong electrostatic force of attraction.
The formation of ionic bond between Na and Cl, that is, sodium and chlorine, can be shown as follows.
Lattice enthalpy. Lattice enthalpy of an ionic solid is defined as the energy required to completely separate 1 mole of solid ionic compound into the gaseous components. Lattice enthalpy of NaCl is minus 788
kilojoule per mole,
which means that 788 kilojoules of energy is required to separate 1 mole of sodium chloride into 1 mole of gaseous Na plus and Cl minus to an infinite distance. This has been illustrated in table 5.1. Covalent bonds.
In 1919, Lewis suggested
that there are atoms which attain inert gas configuration by sharing 1 or more electron pairs with similar or dissimilar atoms. Each atom contributes 1 electron to the shared electron pair and has equal claim on the shared electron. Langmuir called the Lewis electron pair bond is known as Lewis-Langmuir concept. A shared pair of electron is represented as a dash and is responsible for holding the two atoms together. A covalent bond may be defined as follows. The attractive forces which exist due to the mutual sharing of electrons between the two atoms of similar electronegativity or having small difference in electronegativities is called a covalent bond. Steps to write Lewis dot structures. Add the total number of valence electrons of combining atoms in the molecule. Second, write skeletal structure of the molecule to show the atoms and number of valence electrons forming the single bond between the atoms. Add remaining electron pairs to complete the octet of each atom. If octet is not complete, form multiple bonds between the atoms such that the octet of each atom is complete. In anions, add one electron for each negative charge.
In cations, remove or subtract
one electron from valence electrons for each positive charge. In polyatomic atoms and ions, the least electronegative atom is the central atom. For example, S is the central atom in
SO42- and N is the central atom in NO3-.
After writing the number of electrons as shared pairs forming single bonds, the remaining electron pairs are used
either for multiple bonds
or remain as lone pairs. This is illustrated in Table 5.2. Let's go through the rules of VSEPR. Electron pairs arrange themselves in such a way that repulsion between them is minimum. The molecule acquires minimum energy and maximum stability. Lone pair of electrons also contribute in determining the shape of molecule. Repulsion of other electron pairs by the lone pair LP is stronger than that of the bonding pair, that is BP. Trend of repulsion between electron pair is
lone pair, greater than lone pair, greater than bond pair, bond pair. Lone pair.
Lone pair repulsion is maximum because this electron pair is under the influence of only one nucleus, which the bonded pair is shared between two nuclei. Thus, the number of lone pairs and bonded pair of electron decide the shape of molecules. Molecules having no lone pairs of electron have a regular geometry. This has been depicted in Table 5.3. Let us explain the bond angles in NH3 and H2O. Overlap of atomic orbitals. Formation of a bond has been explained on the basis of overlap of atomic orbital having same energy and symmetry. In the preceding section, we have seen that the strength of the bond depends on the extent of overlap of the orbitals. Greater the overlap, stronger is the bond. The orbitals holding the electrons vary in shape, energy and symmetry. So, the extent of overlap depends on the shape and size of the orbital. On the basis of the above consideration, we have two types of bonds, the sigma bond and the pi bond.
Hybridization. Definition. Hybridization refers to mixing of valence orbitals of same atom and recasting them into equal number of new equivalent orbitals, hybrid orbitals.
Steps considered in hybridization. First, formation of excited state. Second, mixing and recasting of orbitals. So let's study the formation of excited state now. The paired electrons in the ground state are uncoupled and one electron is promoted to the vacant orbital having slightly higher energy. Now, total number of half-filled orbitals is equal to the valency of the element in the stable compound. Example, as in BeF2. Valency of Be is 2. In the excited state, one electron from second orbital is uncoupled and promoted to the second p orbital, which has been depicted. Second, mixing and recasting. In this step, the two s and p orbitals having slightly different energies mix with each other. Redistribution of electron density and energy takes place, and two new orbitals exactly same shape and energy are formed. Characteristic features of hybrid orbitals. Number of hybrid orbitals formed is exactly the same as the participating atomic orbitals. They have same energy and shape. Hybrid orbitals are oriented in space in such a way that there is minimum repulsion and thus are directional in nature. The hybrid orbitals are different in shape from the participating atomic orbitals, but they bear the characteristics of the atomic orbitals from which they are derived. Each hybrid orbitals can hold two electrons with opposite spin. A hybrid orbital has two lobes on two sides of the nucleus. One lobe is large and the other small. Covalent bonds formed by hybrid orbitals are stronger than those formed by pure orbitals because the hybrid orbital has electron density concentrated in the side with a larger lobe and the other is small, allowing greater overlap of the orbitals. Types of hybridization and geometry of molecules. Different types of hybrid orbitals are obtained from the atomic orbitals that participate in hybridization. S and p orbitals can hybridize to form the following hybrid orbitals: sp3, sp2, sp. This has been shown in the following diagram. Importance and limitations of valence bond theory. Let's go ahead first with the importance of valence bond theory. Represented by VB. Valence bond theory introduced 5 new concepts in chemical bonding: delocalization of electrons over the two nuclei, shielding effect of electrons, covalent character of bond, partial ionic character of a covalent bond, the concept of resonance and connection between resonance energy and molecular stability. Now let's take a look at the limitation of valence bond theory. Valence bond theory explains only the formation of covalent bond, in which a shared pair of electrons comes from two bonding atoms. However, it offers no explanation for the formation of a coordinate covalent bond, in which both the electrons are contributed by one of the bonded atoms. Oxygen molecule is expected to be dimagnetic according to this theory. The two atoms in oxygen molecule should have completely filled electronic shells, which give no unpaired electrons to the molecule, making it dimagnetic. However, experimentally, the molecule is found to be paramagnetic, having two unpaired electrons. Thus, this theory fails to explain paramagnetism of oxygen molecule. This has been represented in the following diagram. Magnetic nature of molecules. If all the MOs in a molecule are completely filled with two electrons each, the molecule is dimagnetic, that is repelled by magnetic field. Key ideas of MO theory. MOs in molecules are similar to AOs of atoms. Molecular orbits describe regions of space in molecule representing the probability of an electron. MOs are formed by combining AOS of different atoms. The number of MOs formed is equal to the number of AOs combined. Atomic orbitals of comparable energies and proper symmetry combine to form molecular orbitals. Fourth, MOs, those are lower in energy than the starting AOs, are bonding sigma MOs, and those higher in energy are anti-bonding sigma MOs. The electrons are filled in MOs beginning with the lowest energy.
Only 2 electrons occupy each molecular orbital.
And they have opposite spins, that is, their spins are paired. The bond order of the molecule can be calculated from the number of bonding and antibonding electrons. Now let's study the parameters of covalent bond. A covalent bond is characterized by different parameters. These parameters help to understand how strong is the bond between the two atoms, what is the distance between them, and what is the shape of the molecule. Let's study the bond order now. According to the Lewis theory, the bond order is equal to the number of bonds between two atoms in a molecule. The bond order in H2O2 and N2 is 1, 2, and 3 respectively. Isoelectronic molecules and ions have identical bond order. For example,
N2, CO and NO+,
each have bond order 3.
F2, whereas O2-
has bond order 1. Stabilities of molecules can be determined by knowing the bond order. As bond order increases,
bond enthalpy increases and bond length decreases.
Covalent character of ionic bond. Several ionic compounds possess partial covalent character and show properties similar to covalent compounds. For example, LiCl is ionic, but it is more soluble in organic solvents than water. Resonance energy. We have seen that many polyatomic ions and molecules can be represented by different canonical forms, and each form has a different energy. Energy of the resonating form is different from the most stable structure, resonance hybrid. The difference in energy of the stable contributing structure and the resonating form is usually defined as resonance energy. To summarize, it can be stated that energy of the resonance hybrid structure is less than the energy of any single canonical form. Hence, resonance stabilizes certain polyatomic molecules or ions. The average of all resonating structures contributes to overall bonding characteristic features of the molecule. This will be clear from the example of ozone. Ozone can be represented by two canonical forms, as shown earlier, 1 and 2. Third is the resonance hybrid. The energy of third form is less than that of the first and the second. So that was chapter 5 of chemistry. Thank you.